In this segment, we're going to talk about parsing. That's the process of going from a string to an expression, an Expr. And remember, we talked about going in both directions, and we've already covered pretty printing. Now that's the easy one, because in pretty printing, what we do is take a structure, an Expr, and we turn that into a flat string. And we use the structure of the Expr to guide our recursion. But going in the opposite direction is rather more complicated, because what we're doing is we're taking a flat string in which there's an implicit structure due to the grammar of the language, and we're turning that implicit structure into an explicit data type, an Expr. So that's going to be more difficult. We're going to have to work harder to do that. Let's start by looking at some examples of what our function should look like. For example, if we apply parse to the string open parenthesis 2 plus 3 times 4, etc., we would expect to get that add expression with subtrees num2 and that mul expression on the right hand side. If we parse the string with just the digit 2 in it, we'd expect to get number 2, and if we parse a string with just the letter A in it, we'd expect to get a variable A. Okay, so far so good. But what if we parse something like this, the string beginning with 2 plus 3 times 4, parenthesis, parenthesis. The biggest expression we can build from that is num2, because the first thing in there is an expression. But in returning num2, we've lost the rest of the string, which is still to be processed. So somehow we need to deal with that. And I guess the obvious way of doing that is to return not just the expression recognized, but also the part of the string that remains unprocessed. So you can see in the first two examples here, we get an expression and an empty string because the whole string has been converted to an expression. But in the final case, we get the number 2, and then we get the remainder of the string beginning with the plus as the second part of the answer. And then we will further analyze that second part. So that's our guidance here. And we're working in a particularly straightforward grammar here. It's what's called we can write what's called a predictive parser, because we can tell from the first character of any string, any correct string built from the grammar, what kind of expression we're dealing with. So for example, if it begins with a parenthesis, we know it's an addition or a multiplication. Now let's look at how the algorithm works informally. We start off with parsing this expression. What do? We first of all recognize an opening parenthesis. That's there. Then we recognize an expression, which is 2 here. Then we recognize an operator, which is plus or times. Then we recognize another expression, here is 3 times 4. And then we recognize the matching closing parenthesis. So we know what we have to look for in parsing things like this is a sequence: find an opening parenthesis, find an expression, find an operator, find another expression, and close a closing parenthesis. So you can see this is going to be a recursive algorithm. In looking for an expression, we look for 2 sub-expressions as we go along. So let's see how this translates into Haskell. So in this particular part of the parse function, we know we're looking for a parenthesis first. So that's what the first line does. It says, in this case, we're looking at the beginning of an expression. So we're looking at that, and we can see that the rest of the string we call rest. And what do we want to do with that? Remember, we want to now look for an expression. So what we do here is call parse on rest. And then we use this let expression to analyze that, because the result of parse rest should be an expression, E1, and the rest after what remains after doing that parse, which we're calling rest1. So we expect to apply that parse We get E1, the expression, and then we get rest1. What do we do next? We look for an operator. And so we find an operator at the beginning, it's just one character, and then we get rest2. We then have to, after the operator, we have to find another expression. So we call parse again on rest2, and we assume that we break that down as expression2, the answer, the expression found, and rest3. And then what do we expect to find in rest3? We expect to find the closing parenthesis and then whatever is left. And what we return is, depending on whether the op is a plus symbol, we return an add of E1 and E2. If it's a multiplication symbol, we return a mul, paired with what remains after doing all that analysis, what comes after the closing parenthesis, which is rest4. So the algorithm is structured according to what we expect the expression to look like. So what you see here is how you translate the diagram on the previous slide into Haskell. So that covers the most difficult case, looking for an expression. If you want to find the other clauses of the definition, which cover numbers and variables, they're in the file that I shared earlier. But the crucial recursion in this definition is the recursion that you see here, namely using the structure of a grammar to uncover in a string the expression that it represents. And the other thing that we've seen here, just to dip back, we've seen here using a let expression to take the results of a function call, like a parse applied to rest, and to do a pattern match over that result, so that we can name the parts like E1, the expression returned by this parse, and rest1, the bit of the string still unanalyzed. So we've used that construct here. In fact, we could have used a where clause, but it's more straightforward here to use a let. And also the let have the sequence of the pattern matches in the let follow the sequence of the pattern matching against the string. So we first find a parenthesis, then we find an expression, then an operator, then an expression, and then a closing parenthesis. And those follow the structure we're looking for. Okay.